talking about filters by defining a language that we can use to describe them. Filters are a natural follow-on after talking about matching networks because you can think of them as an extension of the same idea. We showed that an L-match lets us absorb energy at one frequency, which is resonance, and reflect it at every other frequency. So we could think of an L-match as a type of filter. That's particularly obvious if we define a transfer function across an L-match network from V in to V out, which would look like a narrow resonant peak. Adding more components in a pi match allowed us to control the shape of that peak and smear it out over more frequencies. So it stands to reason that by adding even more components to our matching network, we could control whether a signal is passed or reflected over a wider frequency. That turns out to be true, and the type of circuit that achieves this frequency response is referred to as an LC ladder filter. We opted to make LC ladder filters out of inductors and capacitors for the same reason we use inductors and capacitors in matching networks, which is that lossless components make the filter lossless. The exact shape of the filter transfer function can be captured by this equation, which we call the filter prototype because it is highly customizable. The epsilon parameter affords some flexibility, but the real special sauce is the Fn function, which represents the ratio of nth order polynomials that varies between 0 and 1 for a while, then flies off to infinity. The order of this polynomial affects the steepness of the filter behavior and the complexity of the filter design, so it's important. It's so important, in fact, that we name filters after it. The order of the polynomial is also referred to as the order of the filter. This is the general picture of what that transfer function might look like. You can see that the x-axis indicates the filter behavior changes with frequency, and the y-axis has units of dB, which means that we're framing our discussion in terms of how much power gets through a filter. That's consistent with the picture painted by our equation, which represents a transfer function squared and accordingly describes a ratio of powers rather than a ratio of voltages or currents. The filter is described by a center frequency omega naught, which sits in the middle of a frequency region called the pass band. The upper and lower edges of this band are described by frequencies omega h and omega l, and they are symmetric about omega naught, so we can specify omega h equals omega naught plus omega p, and omega l equals omega naught minus omega p. There's some loss in the passband, which is referred to as the insertion loss. The transfer function also varies in the passband, and that behavior is referred to as passband ripple. The passband ripple measurement is the difference between the insertion loss and the lowest allowed value in the passband. Some filters have passbands that only ever decrease, which means we can use the vocabulary word monotonic to describe them. Those filters don't have ripple in the sense you might think of it, but we still call the steady decay of the transfer function ripple. In a properly designed filter, the maximum level of passband ripple will occur at the edges of the passband, omega h and omega l. You can pick exactly how much ripple you want to allow in the passband by setting the epsilon parameter, because the Fn function stays between plus or minus 1 in the passband. That means the band edges are usually defined by the point at which Fn equals 1, and the transfer function is 1 over 1 plus epsilon squared at the band edge. Usually, epsilon is set to 1 so that the squared transfer function has a value of 1/2 at the band edge, signaling that the power has been cut in half. You're free to pick how much rejection you want outside the passband, and that quantity is called the stop band rejection. You usually specify this with a quantity AS, so a stop band rejection of 20 dB would correspond to an AS of 10. Stop band rejection is measured relative to the top of the passband. The frequencies at which the transfer function reaches the stop band rejection are called the stop band edges, and we give them the symbols omega sh and omega sl. The frequencies between the passband edge and the stop band edge are called the transition region. Finally, the frequency band outside the transition region is called the stop band. Some filters have finite transfer function values in this region, and that behavior is referred to as stop band ripple. The stop band ripple sets a maximum value for stop band rejection. The picture we've been looking at thus far was a bandpass filter, but the filter prototype can be used to describe all 4 types of common filters, which, as a reminder, are low pass, high pass, bandpass, and bandstop. You can build lossless LC ladder versions of each of these filters, and I've drawn them on this slide. Thinking about the asymptotic impedance of each component can give you some intuition about how the low-pass and high-pass filters I've drawn exhibit the low-pass and high-pass behavior. Consider the low-pass filter as a starting point. At low frequencies, the capacitors are open and the inductors are shorts, allowing the input voltages to reach the load easily, and at high frequencies, the capacitors are shorts and the inductors are open, which zeroes the voltage on the load. Intuition for the bandpass and bandstop circuits requires thinking about the behavior of their LC tanks at resonance. Parallel tanks ring open and series tanks ring short, so the bandpass will have series short circuits and shunt open circuits at resonance, which allows voltages to reach the load. Off resonance, either the inductor or the capacitor will block signals in the series elements and absorb signals in the shunt elements. It's worth noting that all the filters on this slide are third order. They would produce third order polynomials in the filtered prototype transfer function. And that's related to the fact that the low-pass and high-pass filters have three independent energy storage elements, which are the three shunt elements. The series elements in the low-pass and the high-pass filters aren't independent of the shunt elements because they're all part of LC tanks. So in summary, filters absorb power over a frequency band and they reflect it elsewhere. Filters are described by a prototype with that includes a polynomial and a very important polynomial order. Filters have many parameters, which include bandwidth and stop band rejection and insertion loss and many others. And there are four types of filters, which are made by rearranging the inductors and capacitors.